Okay, welcome to Introduction to Mechanisms and Mechanical Systems. We'll begin by going over some course logistics overview. So my name is Professor Jonathan Hopkins. I've been at UCLA for 6 or so years as of this recording, and my contact info is here. If you need to reach me, call me or email me anytime. This is the course's textbook, so please, if you have it, it could be very helpful, but you can get by without it. Certainly for this course, honestly, these videos and the lecture notes that you'll all have access to that I'm showing in these videos are the course's textbook and should be all you really need. However, there is some valuable supplementary reading that I will assign to help you better understand this course. Okay, so in this course we're going to cover these topics. Okay, so we're going to this class today. These few videos are going to talk about the introduction to just mechanisms. I'm going to show some neat mechanisms and talk about some fundamental principles. And then we'll talk about position analysis. That will take quite a few videos. And then velocity analysis and acceleration analysis. Now, it's pretty math heavy up front for these topics. Basically, peaking and acceleration analysis, that's kind of the trickiest. But basically what those three topics will teach you is if you have a mechanism and I give you some kind of input, the angle that the mechanism has been moved to, or the speed that it's moving at, or its acceleration, you can calculate and analyze that mechanism and know all the position of the other beams as well as their velocities and accelerations. So a lot of math, and then we'll move on to rolling contact and gears. And so we'll start looking at more complex mechanisms beyond just traditional linkages. And we'll then do power equations and static force analysis, dynamic force analysis. Those final three talk about how you can calculate and analyze the forces within mechanisms so that you can know if they're going to break. Okay, and you can do some analysis in that regard. So I always like to show this video down here. It's called the Rider Automation. You have the link to it. I'm not going to show it in this video because you can just see it on YouTube, but it's a really great video that shows how complex things can get with mechanisms. There's an awful lot that can be done with mechanisms. Nowadays we usually do most of our functionality with electronics and control and these kind of things, but before there were computers as you know them today, you could do calculations, and there were mechanical computers. And this particular video shows a little purely mechanical doll that you can program what it writes, and its eyes move and its hands write, whatever message you want. And so see that video and it'll show you the complexity of that mechanisms can achieve. And there's still some things today that only mechanisms can achieve. So this course is really going to help you know how to analyze and thereby design some really complex mechanisms that do some really neat things. Okay, so first reading assignment. This is chapter 1. These are the pages from the book I said to get. Again, it's basically supplementary, not required, but very helpful if you have access to the book. Okay. Okay, so let's start out with some basic definitions here. First of all, what is a machine? Well, a machine is arrangement of parts for doing work. A device for applying power or changing direction of motion. Okay, so and first of all, I just want you to point out here, note the emphasis on work, which is things like force and power and these sorts of things. Okay, when we define mechanisms, you'll see there's a little bit more focus on motion and motion paths and these sorts of things. So slight little nuances in the definitions. Okay, Rouleau, a very famous man in this field, he defined them as a combination of resistant bodies so arranged that by their means the mechanical forces, notice that emphasis on forces, of nature can be compelled to do work, notice work again, accompanied by certain determinate motions. Okay, so of course they move as well, but like I said, when you think of machines, think of rigid, resistant bodies moving together to do some kind of work with some force or power. Okay, so some standard parts of a machine is a link, and that's basically a rigid part. Okay, so in this example, this is a classic 4-bar mechanism. It consists of essentially 4 rigid links. Okay, so the gray rectangles here are the links. They're the bodies that are paired together, and they're the things that actually move. Okay, so that's what a linkage. And notice it's not a linkage, it's a link. That's what a link is. Okay. All right, so a joint. What is a joint? Well, a joint is a connection between 2 links. Okay, so the black dots here are the joints, okay, which limits the type of relative motion between the links. Okay, so in this case, these black dots are rotary joints, pin joints, revolute joints. There's many names for them. But they're basically constrain the links, the rigid bodies, so that they can't move in certain ways, but do allow rotations at the center of their axis. Okay, so a joint essentially joins 2 rigid bodies together. They're also called kinematic pairs because they pair 2 things together. Notice the emphasis on 2 in the word pair, and they constrain them to not move in certain ways while allowing them to move in other ways. Okay, so that's what a joint is. All right, so a kinematic chain, okay, this is an important definition. It's the connection of several movable links with joints, okay? So that's what I show here. Basically, when you combine links and join them with joints that can move, you have a kinematic chain, okay? And notice it has to be movable to be a kinematic chain because kinematic means motion, okay? And so in this case, these joints allow a motion. I don't know if you can visualize it, but you'll see plenty of it in this course. Okay? A closed kinematic chain is known as a mechanism. Okay? Closed means that every link is connected to at least 2 other links. Okay? So this is a closed chain. You can see it makes a nice closed loop here, whereas this one is open. Okay? So an example of an open kinematic chain is like a robot arm. Imagine an end effector here that could do something, and it moves around and can pick things up, but it is not closed, and it violates this definition that every link needs to be joined to 2 other links. Okay, and so you can see in this case, this link is joined to these 2, this link is joined to these 2, and so as long as the loop is closed, it's a closed kinematic chain. Every link will be connected to at least 2 other links, which is not true for the open one. Okay? Okay, but we're starting to get to this definition of a mechanism here. But let's talk a little bit more about it on the next slide here. Okay, so mechanism, again, Rouleau's definition. A mechanism, according to Rouleau, is the assemblage of resistant bodies, okay, which are links, those rigid bodies, those bars, connected by movable joints, okay, like these pin or revolute joints, okay, to form a closed kinematic chain with 1 link fixed and having the purpose of transforming motion. Okay, so that definition is really important, and you're going to need to know that, and it has a number of important components to it. Okay, so first of all, let's break it down. So it consists of rigid bodies, or links, okay, that are joined together by movable joints, okay, and 1 of those links must be held fixed or grounded. So in this case, here's a 4-bar mechanism, and in this case, the fixed link is the green link there, okay, so it can't move. But the other critical part of the definition is it needs to be a closed kinematic chain. So you can see, you could draw a closed loop in this 4-bar, was the example from the last slide. And then the final part of the definition is it needs to be able to move. Okay, so we're going to review that a lot and do some examples and you'll be able to tell me what is a traditional mechanism, okay? So this one is also famous. We've talked about the 4-bar, but this is a slider crank mechanism. And of course it consists of rigid links. You can see here there's the ground, there's these 2 bars, and there's this piston that kind of pushes through a prism or translation joint. Okay, and you can see there's a rotational or a pin joint here, and at the two parts there. And so you might say, well, is this a mechanism? Well, it certainly is. It's one of the most famous mechanisms. So let's go through that definition. Well, it consists of links that are connected together by movable joints. Okay, and now the question is one of the links grounded or held fixed? And yes, it is. It's this body right here, which is also basically connected to the that's what joins this moving link to the ground. Okay, and then is it a closed kinematic chain? Now a lot of students get confused and think, no, this is not closed, but it in fact is. And I'll show you a diagram where you could see if we froze this here and drew like a vector loop, it would be a closed kinematic chain. Okay, and so it is indeed a mechanism, and of course it can move. Okay, so let's look at some other kind of definitions, some nuances. The whole field of mechanics is really broken into 2 different parts. There's statics and dynamics. Okay, statics is basically stuff that doesn't move. It's static. Okay, dynamics are things that do move, like these 2 examples on the right here are moving. And that's broken up into 2 different categories within dynamics. There's kinematics, which is the study of motion, and then there's kinetics, which is the study of force. Okay, so we'll really be focusing on the aspect of dynamics, kinematics, and kinetics in this course. Really, the first half is kinematics, the last half is kinetics. When you think of these different topics, if you remember from my definitions, the little nuances, a machine is kind of within this category of, remember, when you think of forces and work, you should think of a machine. And then kinematics is really mechanism. Remember, the emphasis in mechanism is it's got to move. It has to have movable joints. There's a fixed ground, but it moves. Okay, so and you really care about motion paths with mechanism. So this is kind of there. And then structures are static. Like think of a truss in a building. Those are static. Okay, they're not intended to move. Of course, they can deform, but if you load them, but they're intended to be static. Okay. Okay, so let's look at joints or pairs. Okay, so and do some more definitions to help you understand the categories here. So there are 2 kinds of pairs or joints, right? There are lower pairs and there are higher pairs. Okay, and lower pairs. There's first of all, there's really only 6 of them, okay? Or at least there's 6 main ones, okay? And what defines a lower pair is whether the 2 links that it pairs move with surface contact, okay? So it's a little difficult to explain without showing, but higher pairs, for instance, would be imagine a ball on a flat surface. It only touches at a point. That's not technically a surface. Or 2 cylinders, they only touch at a line. That's not a surface. You need to have a surface area. So this is an example of we've looked at this before, a revolute joint or a pin joint or rotational joint, where R stands for revolute. Its symbol can be called R. Okay, and you can see here it's basically a cylinder inside a cylinder, and then there's lips, one on the top and one on the bottom you can't see, and it basically only allows a rotational degree of freedom between this link and the blue link there. Okay, and so you can see it's 1 degree of freedom. That has nothing to do with the fact that it's a lower pair. The thing that makes it a lower pair is that the cylinder is fully touching on a surface, and these 2 lips are touching on flat surfaces. So think of surface area. It's actually got a surface area, not a point or a line. That makes it a lower pair. Okay. Let's look at another example. This is another 1 degree of freedom lower pair. Okay. This is a prism joint, which it translates. Okay. Translational joint, slider joint, some people call it. But prism joint is the formal name. Its symbol is P for prism. Okay, and you can see it's basically a cylinder on cylinder, but there's a key here. And it could be many different shapes. You could have a square inside a square, or just anything that only allows the translation is a prism joint. Okay, and you can see, so it's a 1 degree of freedom thing. It's just one translation that it allows. But again, that's not what makes it a lower pair. The thing that makes it a lower pair is there's surface area contact between the two links that's constraining the unwanted motions and allowing the translation that you want. Okay, so here's another lower pair. And remember, I told you there's really 6. We've done a rotational one, we've done a translational one. Well, now we'll do a helical one. This is a combination of rotation and translation. This screws down with a set pitch, okay? So it's kind of like a helix, so it's called a helical joint or screw, okay? And its symbol is H. And really, it has just 1 degree of freedom because there's threads in here, just like if you think you're screwing a screw into a board or something, it rides down along the threads. But, you know, you may say, well, wait a minute, that's 2 degrees of freedom. It rotates and translates. Well, no, it's 1 degree of freedom because they're coupled. So if you force it to rotate some amount, it's forced to translate. You can't independently actuate the degrees of freedom. And if you translate, it's forced to rotate, right? So and that pitch, the ratio of translation and rotation, is what links it together, okay? And so, but anyway, it's a lower pair, even though it's still 1 degree of freedom with a screw motion, it's still a lower pair because it's surface-to-surface contact. Okay, so here we have a cylinder joint. All right, so this is where, you know, this is another lower pair, of course, because we have surface area contact, you know, driving this. You know, it's called the cylinder joint, so C. But the difference between this and the other 3 I showed you is that it achieves 2 degrees of freedom. You can imagine it could translate and rotate, and the reason there are 2 degrees of freedom is because they can do so independently. Unlike the helical joint that, you know, the rotations and translations are locked together with a certain pitch, this you could independently translate, or you could just not translate, independently rotate, or do them in different combinations. So there's 2 degrees of freedom. Okay? But again, the thing that makes a lower pair has nothing to do with the number of degrees of freedom. Okay? It's just the surface area contact. All right. So here's another one. This is a sphere joint. Okay? It's called a sphere joint or S joint because it's basically a sphere in a cup. Okay? And this is also obviously lower pair because, of course, that sphere has direct surface area contact with the entire cup. And it has 3 intersecting rotations. Okay, so it achieves actually 3 degrees of freedom. You could imagine it could rotate around all 3 of these axes, and really any rotation that intersects the center of the sphere is what it can do. But that results in 3 independent degrees of freedom. Okay, but again, you know, a lot of students start learning in their mind that lower pairs have to do with single degree of freedom joints. It's not the case. It's just surface area contact. Okay, that makes it a lower pair. Okay, so this is a flat joint, and this is the last of the 6, you know, lower pairs. And it's a flat joint because it's a flat on flat, and its symbol is F. And it moves with 3 degrees of freedom as well. It can translate on the surface. You can imagine it could slide in 2 different independent directions, and it could rotate. So any planar motions is what it could do. Now you might say, well, my goodness, you know, I could just lift this right off, and you'd be right, but you would break the joint. And that's a rule that I want to ingrain in your mind, is that you can't break joints. Okay? Not only can they not go through each other, obviously, but you can't lift it off. And of course, in physical world, you could lift it off, but you're not allowed to. Once you separate the 2 links, it's no longer a joint. So when you're analyzing its degrees of freedom, you have to assume it can't be broken. So imagine if you rotated around this axis of one of the translations, you know, one part of it would have to go into the stage and the other part would get lifted off of it. And you can't do that. Well, one, you can't go into it, obviously, but you certainly can't lift it off. That would break the joint. So it's not allowed. Okay? So that joint is a lower pair because it's just surface area contact, and it happens to have 3 degrees of freedom. Okay? So those are the 6 lower pair joints, and they're very famous. Okay? So you should learn them. Okay? But now we get to higher pair joints. Okay? And higher pair joints just have point or line contact. They're not surface area. It's not like one whole surface touching a whole other surface of some geometry. It's just point or line contact. And I gave you examples. And first of all, there are an infinite number of these. Whereas the lower pairs has 6 main ones, the higher pairs, there's an infinite number of them. Okay? Here, if it's two circles on two circles, they just touch at a point, but obviously circles are just a geometric figment of our imagination, but really they'd have some three-dimensionality to it. So if these were cylinders, it would touch along a line. But like I said, if it's a ball on a surface, it would touch at a point. If it's a cam or gear teeth, they touch on a line. And so, well, the gear teeth do. Cams may or may not. Okay, so you kind of get the idea here. Let me give an example of, and again, higher pairs have nothing to do with the number of degrees of freedom. Students start thinking that low pairs mean 1 degree of freedom and high pairs mean more than 1 degree of freedom. It has nothing to do with degree of freedom. Please don't learn that. You'll see I'll give a lot of examples, and they tend to be that way, but it's just not right. Lower pairs, surface area contact, higher pairs, point or line contact. Okay, so here's an example of a pin in a slot. Okay, so you see here's a link, and it's got this slot cut in it, and you've got this other link labeled 1 with a pin, and that slot is slid down on that pin. Now, you could imagine, the way to think about this is that this link 2 is not pressed up against link 1, or it would be surface on surface contact, right? So just imagine this pulled off the pin just a bit, and the pin's really long, and I pulled this forward, so it's not surface to surface contact, but it's just line on the top here and line on the bottom there of the pin. So that's line contact, so that's a higher pair. And when you're analyzing the degrees of freedom, there's two ways you could do it. If you consider it just a planar thing, which is shown here, then it has 2 degrees of freedom. You can imagine if I hold 1 fixed, this could translate in the slot, and it could also rotate. Those are the only 2 degrees of freedom that this could get if it's a planar case. Now, if it's a non-planar case, if it's a 3-dimensional thing, then you could pull it out toward you. You could rotate it in and out of the page like this, so it would end up being a 4 degree of freedom joint. But because we're just showing planar cases, and we're just sticking to planar here for the slide, that's why the slide says it's a 2 degree of freedom thing. Because only things within the plane are allowed for a 2-dimensional joint there. Okay, but hopefully you can see why it's a higher pair, because it's line on and line contact. There's no surfaces touching. Okay, so let's look at different kinds of mechanisms. Okay, let's get back to some more definitions here. Okay, so what is a linkage? Okay, some people call links linkages, and there's totally wrong. So link is the rigid body. A linkage is a mechanism that only consists of lower pairs. Okay, so it has all the conditions of the definition of a mechanism, but it is made of lower pairs. If there's a higher pair in it, it's not a linkage, but it could be a mechanism. Okay, I'll give a bunch of examples later and ask you whether it's a mechanism or linkage. Okay, but by the way, of course, all linkages are mechanisms. Okay, but not all mechanisms are linkages. Okay, so and first of all, since we see these two things, we've already established these two examples are mechanisms: closed kinetic chains, grounded parts, rigid links connected by movable joints, and they move. Right, those are the conditions for a mechanism. But their joints are all lower pairs because they're surface contact. These are all revolute joints, and these are all revolute joints except this one prism joint that the box is sliding in there. Okay, so every kind of joint in either of these mechanisms is a lower pair, so these are both linkages. Okay, so let's define what is a planar mechanism. Well, a planar mechanism is a mechanism where all of its bodies or links move in a common plane. Okay, it's also called a 2-dimensional mechanism. Okay, and so, for instance, if I were to draw, get a marker and put dots on different links that are moving, and I were to trace the path of those dots, if all those dots lie on the same plane, then it's a planar mechanism. Okay? So, and they all move in 2D. You'll see what's not a planar mechanism momentarily, but basically we're going to be looking largely at planar mechanisms in this course. And the extension to 3-dimensional mechanisms is very simple. So by teaching you this in 2 dimensions, it's easier to teach, but you'll easily extrapolate it for any mechanism in the real world three-dimensional as well. Okay, so here's another kind of mechanism. This is a three-dimensional mechanism, but it's a special kind. It's called a spherical mechanism. Okay, so you can see this mechanism here consists of 4 links. There's the gray ground, and then red, yellow, and blue links. Those can move. They're all connected by revolute kind of pin joints, and they can all rotate around these. This red one rotates around this red axis. The red and yellow one rotate around this axis. The blue and yellow one rotate around the other red axis. So everything rotates around those red axes. Okay. The reason it's called a spherical mechanism is because those axes of rotation, those red axes I showed, they always intersect at a common point, as you see there. You see that circled black, outline dot that's white inside. That's where they all intersect. And no matter how those move, if you can visualize those red and yellow and blue rotating, those axes, those red axes may move, but that point of they'll always intersect at the same point. Okay? And that point consequently won't move with respect to any of those other bodies. So if that point was a point on the yellow one, the blue one, or the red one, that point wouldn't move no matter how much the mechanism moves. So the definition I wrote here is a mechanism where all of its links share a common stationary point. And that is the point where all its rotational axes intersect. Okay? If it satisfies that condition, it is a spherical mechanism. And consequently, the motions of all particles or all dots on all of those links will be restricted to be concentric kind of circles, spheres actually, which is why it's called a spherical mechanism. Okay. Okay, so spatial mechanism. What is a spatial mechanism? Well, it's a mechanism where all the bodies or links can move without any restrictions. So it's basically just anything that's not everything I just taught for the most part. Spatial mechanisms are just three-dimensional mechanisms where, if you put black marks on, or get a Sharpie and put marks on the different bodies, as it moves, the path of them may not be restricted to planar paths. They can move in three dimensions, which is why they're called spatial mechanisms. Okay. Okay, and like I said, everything I'm going to teach in this course, you'll be able to analyze and design all of these types of mechanisms. Okay. Okay, so there's another kind of mechanism that's very worth knowing. It's called a compliant mechanism. Okay, and a compliant mechanism basically still consists of rigid links, but they're connected together not by joints that slide and rub past each other and generate friction like prism or prism or revolute joints or helical joints, really any joint I've talked about, but instead they have flexible joints called flexures or compliant hinges. So you can see this is a rigid mechanism, a traditional vice grip here, and this is a compliant version of that vice grip. And it's actually quite famous. Larry Howell made this at BYU, and it's kind of the flagship of all compliant mechanisms. That's why I'm showing this example. But he basically, you can see the similarity between the two. This is just a single monolithic piece, but it deforms at these compliant hinge joints to get the same mechanical advantage as that vice grip there. Okay, so compliant mechanisms are amazing because whereas many traditional rigid mechanisms use multiple parts that need to be assembled, and produce wear and friction and can bind, compliant mechanisms are usually much lower cost. They can be a single piece material, and they don't produce friction or wear or any of these problems. And they just deform at the hinges. So they can be very lightweight, very low cost, and they have all sorts of advantages. So this is a chainsaw clutch. It's made of 3 different parts with a spring put inside. And Larry Howell also at BYU just said, well, hey, let's replace it with a single piece thing that does the exact same thing. And so you can really put a lot of companies out of businesses with compliant mechanisms. So compliant mechanisms are actually my specialty. I teach my grad class is compliant mechanism design. I'd encourage all of you, once you take this course, to take that. I let undergrads take it. and it's it's my favorite course to teach. It's a very powerful theory. And I've actually, because of COVID-19 pandemic and everything, I've launched a YouTube channel that covers the content of that course in extensive detail and with a lot of fun, sensational stuff. So I encourage you to kind of check that out in your spare time to have some fun. And here's the link to the channel, and you can learn a lot more about compliant mechanisms. Okay.